Okay, here we are making video number 6. This is another calculus technique that you can use. This is sort of some basic stuff, a little bit tricky at first, but when you break it all down, it's very doable. What I'm going to try to do is model the path of this through sort of its center line, tracing the curve, and then get a sense of the length of that and possibly the timing of it as well. So what I'm going to do is I'm going to go to my drawing. Actually, this is Copernicus. I'm going to use this in Google Earth. Again, I can do this right here. I'll do it maybe quick. What I'm going to do is make a path, a center path here, just like I'm doing here. And the trick is that with Copernicus, for some reason, you can't save it. And so it's a little bit harder. And I could do that, and then I could take a screenshot, and it would work, but maybe not as well. So I'm going to end that and then go back to Google Earth. Okay, I'm going to click on this and delete that. And then do that same sort of center path. Now, let's pretend that I happen to have some detailed data, or I've got other images or whatever, and I know that every 5 years or something, or every 10 years, depending on how far back it goes, that the extent of this was, 1950, and maybe here it is 1960, there it is 1970. In real life, it's probably going slower. In the olden days, it's unfortunately been speeding up more in modern time. But I'm getting the sense of this path as it snakes through, and then maybe I'd like to anticipate where it will be based on the shape of this glacier that I'm seeing from the satellite image. If I click done, then save to project, I maybe make this red again. I could take a screenshot. If I'm clever, I could take a screenshot with these dots in it. If that represented a time frame, I think you'll see that the moment, I'll go path, the moment that I X out of this, I think I lose those dots. Yeah. Anyway, but I can take a screenshot of this and then import it into Desmos as well. And I'm just going to jump to not have you watch this again. I think it's this one here. So this was the pathway that I made earlier. And you see I went quite a bit farther along. It's quite an elegant little curve. What I'm going to try to do is I'm going to try to model this using our parametric equations. Okay, so if you recall, parametric equations are when the x coordinate is controlled by one function and the y coordinate is controlled by another function. So what I did was I just went through and made a series of points. I did not make an effort at getting these like by decade. In fact, but I would encourage you to maybe try to do that, because each data point then would represent the same time frame, and that is the beauty of parametric equations, is you get that ability to track things over time. Then what I did was I took those data points and I put them into an Excel sheet, and here it is. That was it highlighted before I pasted it. So these are my x coordinates, these are my y coordinates, and now here's my t. In fact, just to make it a little bit clearer, if I insert a row above right there, this would just be x, this would be y, this would be then t, and then this is my x. If you see over, that's the x coordinates with the 81, and this is t, and this is the y coordinates. Okay, and then if I just clean up where that's going, we can see it a little bit more easily. I just gave myself a little bit of a buffer here just to make it a little bit more readable. All right, so what I did is then I copied this set of data, and then I put that into a separate Desmos, and that is right here. Okay, so these are only the x coordinates, with the t coordinates being my 1, 2, 3 on up. So I just numbered my time points, and then once you graph them, you can fit in a regression equation. And look at that, with between a linear, cubic, quadratic, cubic, quartic. You can even go to 5th, 6th, 7th degree. You can find regressions that match your data pretty well. This is then that function, and I'm going to turn the black off so you can see that my red function matches that my green data points for the x coordinate only pretty carefully, pretty accurately. And here is the y data. Those are what my y coordinates are doing. And then here's my quartic regression. Maybe not as perfect, but pretty good, pretty good. And then what I can do then is copy down these two functions. Here's my g function. I'll turn this red one off. And you see my f of x is my x coordinate, and my g of x is my y coordinate. I can then take and copy and paste those into that parentheses form that's for parametric. Okay, so this then is my parametric form. Why can't we see it? Because remember, this is made to get data that's out 200 and 400 meters. Okay, so this is way off screen. But if I copy this and then go back and I've pasted it into this one here, and if I paste it here, you can see there is my parametric equation. This is the cubic form, the negative 1.27. If I go back here, you can see right up there, there it is, negative 1.27. This red function, that's the negative 1.27, then x cubed. So I can make this black parametric model my my glacier movement. It's not perfect, but it's pretty good. I could spend a little bit more time tweaking it probably. You'll notice down here though that my first data point is at 1. I have a total of 9 data points, so t goes from 1 to 9. If I make this go from 0 to like 11, you'll see that it goes much farther. Whoops, 11. There it is. So that's the extent of that, but I wanted to only mimic the the glacier, so that's why I chopped it back to 1 and 9. Okay, so what can I do with that? Well, I can use my calculus skills to model it over time in finer increments, but then I can also use arc length to determine the length of that arc. And then I can compare that to what the computer has given me in my measurement. If I go back and I can see, does it work? Is it accurate? When I click on this, what does it say the arc length here is? It looks like it's just over 3 kilometers, 3,000 meters. Okay, so there are some data crunching skills you can use. Good luck.